Well, good afternoon. Welcome to Chem 401. We'll start with a brief commercial. Uh-oh, can't play. Maybe we won't. That was a waste. Ah, well, we'll start that another time.
Ooh, did you go to the brick test?
Yeah, I did.
I know, I feel it.
That's like so sad. You definitely get where you're buying. If I'm feeling that. Yeah, a couple hours of sapphire.
We'll have that commercial next time. Where were we? We were talking about nuclear chemistry, and we talked about something called radiocarbon dating. Had we figured out, oh, and we actually did another example on page, there we go. We've done a couple of examples with the fact that all nuclear reactions have first order array laws, first order integrated array laws, and then we've done radiocarbon dating and figured out how long it had been since the plant died, 2.1 times 10 to the third years. Is that about where we left off?
Yeah.
So radiocarbon dating, so with the half-life of carbon-14 being around 5,700 years, it is good for things that are about 2,000 years old to maybe 25,000 years old. But certainly things around our Earth are reported to be much older, and so you might want to date things that are even older. One of the techniques is decomposition of uranium-238 to lead-206. That is, I think it's a 14-step decomposition, but yeah, there are many steps involved, but the overall half-life is 4.5 times 10 to the 9th years. Similar to radiocarbon dating, if the half-life is 5,700 years, it can date things in and about that range. If the overall half-life for the process is 4.5 times 10 to the 9th years, it can date things of about that age. And it assumes that there was no lead-206 in the rock that contained the uranium-238 at the beginning of the process. And if you remember, there are certain assumptions to go into these calculations no matter what. And this is one that goes into the uranium-238. So all of the lead was original uranium at time equals 0. So the starting amount of moles of uranium would be the sum of the current moles of lead and uranium and the current moles of uranium. Oh, this one went back to the beginning. Let me move that on. So, for example, a meteor contains 0.556 grams of lead-206 to every 1 gram of uranium-238. Determine the age of the meteor. So the idea is that we're going to have to figure out, we're going to have to turn the moles of lead, or turn the grams of lead into moles of lead, add them to the moles of uranium to get a total moles that must have been there at the beginning. And let's say this. So let me put it another way. The moles of lead is the moles of uranium that have decay. And the moles of lead plus the moles of uranium is the moles of uranium emission. Now we have 0.556 grams of lead. And we're going to convert that into moles. From the periodic table, well, actually not from the periodic table. We know this is lead 206. That means that the mass of 1 mole of lead 206 is going to be 206 grams. Well, note that it says 207 on the periodic table, and remember those numbers on the periodic table, and this goes way back to Chem 300, maybe the very beginning of Chem 400, are the average over all naturally occurring isotopes. So this is just one of the isotopes. But that's why I'm going to use 206 here, 206 grams, because it's lead 206. And I'm going to go ahead and put in my 206, if anything. Well, we get 0.00270. Moles of lead 206. And now I'm going to do the same thing for the uranium. I'm going to turn it into moles. And I get 0.00420. And now I'm going to plug it into the first order integrated rate law. Since I have masses, I'm going to use, from last time in the notes, the n values. N was mass. I said you could use rates as well. Where the mass of So here's what I did. I made a mistake in my notes, and let me see if I can work it out. So this is how much decayed away. But this is not the amount that decayed away. This is the amount that's left. So the amount left at some time over the initial amount. So here's what I need to do. So n sub t is the amount that's left, and that's going to be 0.00420. That's the amount of uranium that still has to left to decay. The amount that was originally there is going to be the sum of these two. So the lead was uranium, so when I add these up, so 0.006. All right, I'm a little bit out of space here. Hopefully you have a little more space left. I'm going to finish up over here. Now I've got my two numbers. I have my half-life. I need my K value to plug into this equation. K is 0.693 over the half-life. for my K value is 1.54 times 10 to the minus 10. And now I'll plug into this equation because I have my N of T, my NO. And that's a T right there. Let me get my handy dandy calculator. And I get T equals 3.22 times 10 to the 9. Yes. So, apologize, I had to do that on the fly, but any questions about this example? Yes. N sub O? Sure. So, 3.22 times 10 to the 9th years ago, there was only uranium-238. Okay. And then whatever decayed into lead, so it created this amount of lead. It wasn't exactly the same, and that's why I chose to do moles, right? Because I knew I couldn't use the grams of lead. I had to convert it into something that was the same here. So I chose moles. Does that answer your question, though, or I can go through it? All right. Any other questions? Okay. If not, then we'll continue. Two mass-energy relationships. And we covered this a little bit last time, law of conservation of mass plus energy. So mass of energy before reaction, or sorry, mass plus energy before reaction equals mass plus energy after reaction. This is a statement that mass plus energy is conserved. We gave the equation last time, I'll give it again. Energy equals mc squared, where energy is in joules. Mass must be in kilograms, and C is the speed of light, the speed of all electromagnetic radiation. One of the reasons we're so interested in this is that you can use nuclear reactions to generate energy, large amounts of energy. If we were to look at just 1.00 gram converted from mass into energy, well, we'd have to convert that 1.00 gram into kilograms, so we'll move our decimal point 3 places, 0.001. Plug it in, it's simple, so equations given on your conversion equation sheets, and it will be for your third exam and your final. Plug this in, 9.00 times 10 to the 13. Wow, that's a lot of energy. Of course, the trick is how do you do it? But if you can do it, for sure, you get a lot of energy back. So now let's talk a little bit more, or a little bit about how you actually do it. And to do it, you have to do a nuclear reaction. And we're dealing with the binding energy. This is going to be the binding energy of nuclei, of the nucleus, the particular nucleus. And you have to do, like I said, a nuclear reaction. So the energy that holds nucleons together, and I'll define nucleon. A particle in the nucleus could be a proton, could be a neutron. Of course, we've also seen that protons and neutrons can break down into other particles, but we will just do nucleon, a particle in the nucleus. And really, practically speaking, protons and neutrons. So, and the energy that holds those nucleons together is called the nuclear strong force. The higher the binding energy, the more stable the nucleus. The mass effect is the loss in mass that is converted to energy that occurs when protons and neutrons combine to form a nucleus. So, lost mass is converted into energy. Binding energy is usually expressed on a per nucleon basis using electron volts as the energy unit. This not something that I am that worried about, meaning on a per nucleon basis. I'm mostly interested in getting across the point that there's lots of energy in these reactions. And does anybody know what my favorite energy unit is? Joules. I'm a joule man, right. And so we're going to keep it in joules, sometimes kilojoules, because for me, what we need to know is how these energies compare to the energies that we've been dealing with the entire 2 semesters, some of you, and certainly this semester. And chemical reactions have energies in terms of kilojoules per mole. Let's see. So this is here, but we're going to keep our answers in joules per mole or kilojoules per mole. On the homework, you might see something that goes all the way to mega electron volts per nucleon, but you won't see it on the exam. All right. So to do this, though, we're going to have some basic mass values. And the mass of one electron, or what's that? Sorry. Let's just say mass of electron is going to be 5.486. Times 10 to the minus 4th grams per mole. Mass of protons, and I'll point out that mass of proton, we can just use P. If they're in a nuclear reaction, there's going to be a 1 and a 1 here, but either case are my abbreviations for protons. Mass of proton, 1.00728. Grams per mole. And mass of neutron, is going to be 1.00866 grams per mole. And those numbers are given as well, but Now, we'll do an example. And I believe, does it say the molar mass in your notes? Because I think in red is something I changed. What does it say in your notes?
Atomic mass.
Atomic mass. That's another change I'm going to do, again, because we're comparing into chemical reactions. And since everything's in terms of grams per mole, I'm going to do molar masses instead of atomic masses. I'm happy to do things in other ways as well, but my goal here is to, in short, cut to the chase and get to the useful stuff. For the more useful stuff, depends on who you are. All of these things are useful to some scientists. All right. So calculate the nuclear binding energy in mega electron volts per nucleon. We're doing joules per mole for iridium 194. So I'm realizing one other thing that we've got here. No, this is right. So this is, my question I was just thinking about was, are we going to include the electrons in this? And since we're doing grams per mole, we are going to include the electrons even though we're focused on the nucleus. Inside iridium 194, how many protons are there per nucleus? 77 protons. Then the difference between these two numbers is going to be the number of neutrons. And we have 117 neutrons. And 77 electrons. So the next thing I'm going to do is I'm just going to add up all the mass for these. So 77 protons is going to be 77 times the mass of a proton. (117) times the mass of the neutron. And times mass of electron, 5.486. And this is going to be the general process. You're going to add up the masses of all the different particles. And when you add them up, you will get that the mass of this is 195.616. That's the mass of all the particles. This is the mass of 1 mole of iridium 194. The difference in mass is the mass that has been converted into energy. So I'm going to subtract off the grams per mole. And the difference in energy, and I'm doing it on a per mole basis, the difference in mass is going to be the mass converted into energy. And that is the energy, the mass converted into energy to hold those nuclei together. A is the plural form since we're talking about a mole of nuclei right now. There is only one. from here, 1.651 grams, I want to use E equals mc squared. I have grams, I'm going to convert it to kilograms by moving my decimal point 3 places. And I get 1.49 times 10 to the 14th. So a ton of it. And just to make one or two more notes here. So this number is the actual mass of a mole of atoms. This is the mass of all the parts. Of atoms in mole. It's not a big mass difference. You have to be very careful when you add up your parts to find this mass, but certainly once you do, it adds up to it. Any questions about that? Yeah, Logan. What is the matter that makes up that mass?
Because you still have the same, theoretically, you have the same number of particles in iridium-194 as the particles we've added up. So we haven't lost any particles, but we lost mass.
That is a very good question. So where did we lose the mass from if we still have all those particles? So first answer I have is I'm not 100% sure. Second thing I would say is that when you get that many of those particles that close together, things probably change about each of the masses of those particles. I'm not sure what that means though. The analogy I would come up with is if you think of physics and if you go back to the Big Bang, right, and you try and cram all the mass of the universe into a tiny point, like at singularities, weird things happen, and this is close enough to a singularity, just forming each atom, that I think the details become a little sketchy. They change. Like the rules bend. Which I know is not a good answer. It's a good question. I don't know. It's an interesting thing to think about. Well, so what can you expect on your third exam? Since this is on it, you can expect some type of calculation where you're doing an E equals mc squared, probably for some type of atom that is smaller than this, although who knows. And you'll be given the information for the masses of each of the types of particles, and you'll be expected to add it up. Although, as we go through, you'll see there's a couple different situations we can use this. David, and then.
So are any units for this example were joules per mole? And the last one was just joules?
Yes.
So is it just intuitive whenever we're doing questions like this, where we're involving grams per mole, that the ending energy will be joules per mole?
Yeah, well, so I told you to put it in joules per mole, although I did have to change. And the last one, I calculate the amount of energy in one gram change, and so you would be that would be either just joules or joules per gram.
Okay, so we just
yes,
squeezed in at the end because you wouldn't be able to squeeze moles in doing the E equals mc squared equation, could you?
Right. Where do so moles? We had grams per mole. and then we just worked with the grams, and then we put the moles back on. Is that, yeah. So then we knew we had this many grams per mole, so we just worked that through the equation. So yes, that is how we.
And will the mass of each of the electrons, protons, neutrons be available?
Those will be given, yeah. The mass of each of the particles will be given. And I mean, if you look at this, the mass of the grams per mole of the actual type of nucleus, yeah. So pretty much, as long as you know to add them up and how to work with something like the nuclear solution. That's the thing. Question, Marissa. So the question is, how would you get this number that precisely? You would have to create this isotope in enough of it to weigh. And I have to and if it's non-radioactive, if this is a stable isotope, then that's easy. If it's stable, you can either go dig up a sample of this isotope, or you could make this isotope and then weigh it. So you would need a sample of this isotope. So a question, shouldn't you be able to add them? Is that sort of your question? And the answer is, one would think so, right? But no, and I mean, I think, okay, so in chemistry, we talk a lot about when a reaction is endo or exothermic, because we could do endo or exothermic reactions in the lab, and we can measure the changes in energy. And so those are sort of chemical reactions. And then we can start doing things like you have a positive and a negative charge. If you're in your physics class, you can start to calculate, or we even mentioned Coulomb's law in here, right? We said we can calculate the energy between a positive and a negative charge. And so this is really the first and only time that we're going to talk about what holds nuclei together. And it is a different thing. I don't even know, but when you get into physics, or what's this, when you talk about chemistry, there's protons, neutrons, and electrons. But there are a ton of other particles as well. And some of them are in the nucleus and allow this type of thing to happen. But I actually don't know. But you're right, I would think you could take, the total is the sum of the parts. Not true. Why? Because if you think about it, you have 77 positively charged things in a space that is 1/100,000th of a, of a nanometer, right? And it needs a lot of energy to hold it together. I mean, I think another interesting question is, how in the world does this work? That you can get that much positive charge when I can't even force two magnets with the same polarity together. Right? It is a different type of force. And actually, I don't think it's very well understood. I could be wrong about that, but I think there's a lot of stuff to do about, and you hear about a grand unification theory of the forces, and you'll see that the strong nuclear force is always outside. Right? We can put everything else together: gravity, electrostatic forces, and then well, okay. here's the strong nuclear force. Anyway, so these are good. These are great questions. I don't know if anybody knows the answer. I know I don't. So, but it's good. Right. These are great questions. What's that?
It's the realm of quantum physics, isn't it?
It's the realm of quantum physics, and even I don't even know quantum physics. I mean, sure, it's quantum. I was going to say quantum mechanics, which we talk about, is basically electrons.
Yeah.
And then, because that doesn't even hardly get into electrons. Anyway, so I don't know. Any other questions I cannot answer? No, and Well, so and we've talked about this a lot. There are so many questions that I don't know the answer to that encourage me to find them. I mean, I can do research for years about coffee, right? And that you'd think people would understand how to make a cup of coffee. But I'm going to do research on coffee for years and hopefully involve my students. So, all right. Next topic is fission and fusion. And so I guess since I'm on a rant, I might as well keep going. So if these are the kinds of questions you're asking, then you should be going to graduate school, right? So where you can learn more than anybody else in the world about something that nobody else in the world cares about, which is not exactly true. But it's smart. And I have the thesis to prove it. So I think I might be up to my toes on how many people have read my thesis so far. Anyway, and I'm happy to talk about grad school, but let's get back to this. So fission and fusion, so the greater the binding energy per nucleon, the more stable the nucleus. This is binding energy per nucleon versus mass number. The most stable nucleus is nickel 62. We used to think it was iron 56. That's why iron 56 is pointed out on this plot. But it is recently been found that nickel 62 is more stable. Heavy nuclei gain stability and release energy if they fragment to yield mid-mass elements. And basically what these are saying is that here is the most stable region on the periodic table. If you're heavier than it, then fission is going to be the breaking up of bigger nuclei to become smaller. Why? Because they get more stable. Fusion is going to be taking smaller nuclei and fusing them together. Why? Because they become more stable. Even for nuclei, it's the same thing as for electrons. Everybody's trying to lower their energy. It's a little bit harder in general to do than for nuclei than for chemical reactions with the rest of it. What have I said? I have said that we don't have to work with the stability and whether how reactions happen. We just have to be able to write them. Anyway. I don't know if I should even ask if people have questions about this book. All right, so a little more about the details that we will go into. Fission, the fragmentation of heavy nuclei. Nuclei break into fragments when struck by neutrons. It doesn't occur in exactly the same way each time. For example, uranium-230, so it's 235. The example I have, though, in my notes is uranium-238, more than 100 different fission pathways. This is going to be a nuclear transmutation. Or a type of nuclear transmutation. And nuclear transmutation is different than radioactive decay. Radioactive decay says one type of nucleus spontaneously breaks into two or more parts. This is going to be a collision is involved between one nuclei, and it could be anything really, but it will typically be a collision between one type of nucleus and a neutron or an alpha particle or some type of particle. This is going to be a collision between uranium-238 and one neutron. And the word that I often use for this type is that uranium-238 is bombarded with neutrons. Bombarded with neutrons. problem on an exam, if I say uranium-238 is bombarded with neutrons, you will write these two reactants. It will then say, producing Te-137 tellurium, yeah, selenium tellurium. Tellurium-137 plus 2 neutrons. Plus another nucleus. And so your goal is to use our rules for balancing nuclear reactions to show that we get 239, 138. Oh, sorry. There are 2 of these. So we get 100 at the top, 40 at the bottom. And then this is element number 40. Where's the other nucleus? So that is a fission reaction. Question, Mackenzie.
Does the index have to do with, like last semester we learned that as you go down the periodic table, was it like people don't get less time held? Is that kind of why they go down the bracket?
Good question. So, except for nuclear chemistry, everything we've done for 2 semesters in 400 and 401 has been about the electrons. Now, we essentially are not talking about the electrons at all. Which is weird, I know, but, and that's why all the trends that we talked about for chemical reactivity don't matter now. And that's why I'm not concerned with trends. Because all we're talking about is, all right, so you take a specific type of nucleus, uranium-238, you can dig this stuff up and purify it. It's in, I think I mentioned, Moab, Utah area. You purify it, and then you create a neutron beam. Not that easy to do, but can be done in many places around the world. And so you basically hang your uranium there and aim your neutron target. And what you might imagine is that hitting a nucleus that is 10 to the minus 5th nanometers across, not that easy to do. But the rules are all different for nuclei. That's why we're not remembering any rules for nuclei. I don't know if that makes like yeah, there are trends for the electrons, and those are super important. These, we want to understand more about the energy. Yeah, hopefully that answers. Kate? Yes.
Is that 100 is 137? Yes, 100 is 152 is 8, right?
So I have 238 plus 1, which is 239. I have 137 plus 2, which is 139. I need 239, so I put 100. So the so like I could have also written two different ones. The 2 is a coefficient.
So it's like
It just means to add up 2 of these. Marissa?
how did you know it's like
Great question. How would I know, or more to the point, how would you know? And the answer is you wouldn't. There are many different fission pathways. It would all be given except for the zirconium. Yes. Yeah. And you know, there are some trends in radioactivity that we're skipping. Who knows how this is going to come about? I have to give you everything but one of these because there are more than 100 different pathways when you do this type of stuff. So, does that answer your question? Right, so it seems like a lot of different nuclear reactions that there are that you could write, and there are, but the underlying principle here is I have to tell you everything except for one of them for you to write it. And maybe the new thing here is that there's 2 of these, so you have to multiply this number by 2 to do your balance. Question?
No.
Or too many questions?
It's just about nickel being unstable. I just don't understand why would it be a smaller element? Like, why would something in the medium range have like a strong force? If you figure the less things you have in there, the easier it will contain them.
Yeah, no, so why, why nickel, why iron? So as an engineer, you would have to get into it a lot to figure that out, and then, what is the usefulness of it? So,
And then those are also 2 green base or magnetic property atoms that have a
they're also right. They're also ferromagnetic materials, right? So, and you can start to put things together, and there's a whole area of chemistry and physics around this, but. Iron is one of the smallest atoms too. And what does that have? So the electrons are held tight. Lots of good questions though. All right, so. Okay. So now we're going to talk about uranium-235. This is the one that is typically used or one of the ones that can be used for nuclear power. And it can be used because there's such thing as a chain reaction. I would like to define a chain reaction. It is a reaction that continues even if no more neutrons are added. So, for example, you see a neutron coming in. It breaks this uranium-235 nucleus into 2 pieces and 3 more. Those 3 more initiate 3 more reactions. And this is actually the definition of a exponential process, because you get 3, and then you get 9, and then you get 27. And another part of this is, for a chain reaction to occur, you have to have what's called a critical mass. Definition of critical mass: a mass of nuclear fissionable, it could be fission or fusion. So I'll just say mass of nuclear material necessary for a chain reaction. The idea being that if you have enough uranium in one place, if you have a critical mass of it, then you put in some neutrons to get it started, that it will break, there'll be more neutrons, and you can actually get this to exponentially increase and explode. And so this is a nuclear reaction. If you have a critical mass, you can have an explosion. Question, Logan?
Is that mass just the amount of molecules that you need to have a high enough probability to strike them when they're
So you're on the. I'm not exactly sure what that mass is, but you can imagine that once this first reaction occurs, then if these 3 hit a certain number, it could be 3. I think it could even be 2.5. And then they keep going, and as long as they keep expanding, the reaction will get out of control, and the chain reaction is above the critical mass. And the way you control this kind of nuclear reaction is one of two ways. Between some of the uranium-235 and the rest of it, you put substances that absorb neutrons, or you just space the uranium out. But it is the key concept is how do you control this reaction to generate the energy without having to waste it. So from the top example, which one would it be? Oh, it'd be the uranium-235, right? Because these three would then do, basically, would come back and do the reaction again with the uranium-235. Any other questions? Yeah.
So when they refine uranium, the challenge is then preventing it from spontaneously showing itself.
Yeah, so yes, the problem is, keeping it, so, because the other thing is uranium-235 is also radioactive. So the nucleus is breaking down all by itself. So there are many challenges associated with this, but yes, you don't want to get too much uranium in the same place no matter what until you're ready for it to go critical. And even then, you're trying to balance, because you want it to go by itself. You don't want it to get out of control by itself. And it's actually, so more is coming up with this. So fission of 1 gram produces a ton of energy. Some countries generate as much as 80% of their power through nuclear fission. And the products of fission reaction are themselves radioactive with very long half-lives, which is, of course, a big environmental. Why would people do nuclear fission, get their power from nuclear energy? Does anybody have any ideas? Travis?
It doesn't care.
No pollute, well, let's say this.
Yeah.
No greenhouse gases,
Yeah.
or very little greenhouse gases. Anybody else? I might have mentioned it. Anybody else know the other main reason?
Hard to use.
The weight is sustainable.
Hard to use, but if you could, you can get a lot of energy. Is sustainable. I would say, I think there are a lot of advantages. I think that the main other reason I see to do nuclear power is you don't have access to other forms of energy, right? So this number, 80%, I think it's actually 78% last I heard for France. Like if you wanted power, and you could not go to places in the world that had tons of barrels of oil and extract it, then, and you want it, I would say that this provides relatively cheap, plentiful power, right? And that helps your economy grow. I mean, that's what we have in the United States. I mean, how much is gas now per gallon for a car? Just went over $4 a gallon. Do you know how much gas costs in France?
A lot more than that.
Yeah, it's like $4 a liter, and there are 4 liters in a gallon. Right? It's probably not that bad, but it is really expensive. Why? Because they don't have the access to it that we do. And I mean, and so if you open up more space in the U.S. to drilling for oil, drilling for coal, that keeps energy cheap in this country without having to do nuclear energy. So it's a very complex system. But eventually, people say we will run out of coal, we will run out of oil, we will run out of shale, natural gas, and I think we will still have nuclear power as an option.
This is kind of a question about like nuclear power plants in general, but as to my knowledge, remember the Fukushima accident that happened? Wasn't that power plant completely designed differently than the ones in Europe, where like there's a fail-safe mechanism where like the fission can be stopped if these rods fall down in the event of a meltdown, but that wasn't the case in Fukushima. It was built differently, so that didn't happen. Or do you know that much about it?
So I do know a little bit more. So I know that that GE has been investing in nuclear power for years to design safer, better nuclear reactors with this idea that we had to come back to it at some point. And so far they've lost. They've invested millions of dollars, billions of dollars in this, and the public image cost is still too expensive. But if gas was $9 a gallon, $12 a gallon, right? And all of a sudden people might start buying electric cars, right? And so I don't know. I think there's a bigger picture too, and maybe we're not there yet, right? In California, we're shutting down all our nuclear reactors, right? Now there are valid reasons to do that, but one of them might be California privilege, which is we can do it and still get everything else we need. But I think I think there's a lot of other issues, but there are a lot of problems with nuclear power. I don't want to say that at all. So anybody who lives in the Chernobyl area or did live in the Chernobyl, anybody who lives within 50 or 100 or even more miles of the Fukushima plants, I mean, it doesn't matter what we say about cheap energy. They have had to move away from their homes. So, anyway. Where were we? Oh yeah, so there are big environmental problems. So the fuel, just a little bit here, nuclear reactors, it's uranium-238 enriched with 3% uranium-235. It's too low, that concentration is too low to go supercritical. And let me put this one up and then put the next one up too, because it should have a picture of the process. There we go. So, because what we've said so far is just that these reactions generate an enormous amount of energy, an enormous amount of heat. This has to be done near a large body of water. And what you actually do is you actually turn water into steam, use that steam to pump a turbine, and that's how you get your electricity. And there's a lot of excess water, a lot of steam and a lot of cooling to keep everything from overheating. And so you'll find nuclear reactors on large bodies of water typically. I don't know about, does anybody know about Rancho Seco, the nuclear power plant that was in SMUD? I don't know what large body of water is. But I think thinking about how you actually turn all that heat into actual electricity. I mean, this is how all power plants work though. When you burn natural gas, it boils water. That water, which creates steam. Steam goes through a turbine, turns it, that generates electricity. Coal, and that's how it works. Any questions about this? It's pretty cool. It's a very old-fashioned process, and the only question is how are you going to heat up your water? Right? Or, okay, so how did they do it before they heated up the water? They put it near a river and they turned the water wheels, right? It's basically the same way they've been doing it for a long time. What's the new way to do it though? You're still turning stuff. Wind turbines. Solar panels is actually different because solar panels, they turn the heat into the electricity directly. So, fun to think about how we make energy, right? I didn't mention the control rods, so but yeah, I think there was a question about how do you stop or slow down the reaction? You have control rods. Okay, well, let's say it does get out of control. How do you make an atomic bomb? I mean, it's the same reaction. You just allow it to get away from yourself. And so I thought this was pretty cool. So So same reaction we've been talking about. You'd have a chemical explosive that drives two different subcritical masses of uranium-235 towards each other with enough force and enough energy to create a critical mass that will then go out of control. So it's a bomb within a bomb, pretty much, because that's a chemical explosive. So assume uranium-235 decomposes completely by the following nuclear reaction. How much energy is produced per gram of uranium-235? Let's see, so in this particular one, we're going to take the reactants, add up their masses, take the products, add up their masses, so reactants. That's definitely a rough calculation, but it will provide an interesting idea. So we know the mass of a neutron. Uranium-235 molar mass going to be very close to 235 grams per mole. 235. And 0.043943. 141.916, etc., is going to be the molar mass of barium. Krypton 91, 90.923. I get 236.05260. And I'm going to change my units from grams per mole to just grams because I'm adding up all the different particles just to get a total mass. So just grams. And if you plug this difference into E equals mc squared, which is by now, I think, the third time we've done this, you get 1.7 times 10 to the 13. Assumes everything. Yes, assumes all of it goes to this reaction, which. Right, so the difference between these two. What you had at the beginning, what you had at the end. And like I said, there are over 100 different possible pathways for, like when this nucleus breaks down, it doesn't have to be these two, but it does have to add up to the same mass numbers and protein numbers. No, so good question. So there are no neutrons. I would have to think that the chemical explosive when it jams them together, I'd have to think about that. Uranium-235 is radioactive, but you're right, I don't know where the neutrons would come from. Unless unless enough neutrons were kicked free through the collision, but that doesn't make any sense either. I'd have to think about it. They may not give away those details in the pictures. There may be
We don't want to
neutron
make
source.
nuclear bomb.
Yeah. We could write a book. All right. So nuclear fusion. So there's two things. So far we've talked about fission with an FISS ion. This is nuclear fusion. The joining together of light nuclei. We said this happens just like fission. Fission was making bigger nuclei smaller. Fusion is making smaller nuclei bigger to get to that most stable zone. Also releases enormous amounts of energy. Fusion of hydrogen nuclei could be a potential power source. And hydrogen isotopes are cheap and plentiful. Fusion products are non-radioactive and non-polluting. You're making helium, which, by the way, we're running out of. So if we could solve this problem of fusion occurring, we would solve another problem as well. Technical problems to achieving a practical, yes. So the temperature has to be 10 to the 6th Kelvin, which is not something that you can have any materials that really survive. This is the technology of the hydrogen bomb. And for hydrogen bombs, you would use an atomic bomb. So to make a hydrogen bomb, I guess the picture would be conventional explosive pushing together fissionable material, which then push together enough material to make a fusion or atomic bomb. And so it gets more complicated. But it takes more energy and higher temperatures to do it. That's what I want to say about this slide. A little more about the process, because it all comes down to nuclear reactions. The other thing about fusion is that the temperature needed for fusion is achieved in stars. And so fusion is what powers our sun and other stars. So it is possible. You just have to be a star. Not that you're all not stars. But you can't do fusion. All right, so
You can't do fusion. So like you are.
I know. So fusion reactions in the sun, and this is going to be a summary. It is more complicated, but this is a fairly nice one. Take two hydrogen atoms. At the temperatures that we're talking about that fusion can occur, they will fuse. Into hydrogen 2. It's not balanced, is it? What else do we need? I don't know, but it's got a 0 on the top and a 1 on the bottom. And it is a positive. Which is a positive electron. That's one of the particles we've come across before. Then, to continue, one of the hydrogens in the sun then collides with the hydrogen 2. Hydrogen 2, by the way, that's an M at the end there, is called deuterium. Deut meaning 2, hydrogen, deuterium. If you've got hydrogen 3, that's called tritium. Tritium, pretty highly radioactive. Can start to make helium. That is what the sun is making. It is making helium. It makes helium-3, at least to start here. Both of these reactions happen twice. And from there, you fuse 2 of the helium-3 nuclei. Into a helium for a stable nucleus plus 2 stable hydrogen nuclei. And if you come up with the overall process, you will see it adds up to 4 hydrogens. Well, let's see. I have 1, 2, 3, 4, 5, 6 hydrogens. 2 of them are canceled out. 4 hydrogens become helium-4, which is the common form of helium plus 2. Anyway, that's a brief summary. What you can then do is you can add up all these parts and show that there's a tremendous amount of energy produced by this process. What do you have to know about this process? Well, potential. So again, for fusion, you don't know anything except if I give you all of the parts except one, how to put the last one in. And then if I give you, I could ask you a question about E equals mc squared about this, where I give you the masses of all the reactants, the mass of all the products, and ask you to calculate the energy based on the difference in mass. Any questions? Now, we've talked about nuclear transmutation before, but we'll come back to it now. Is that basically what we said is nuclear transmutation takes 2 things on the reactant side and collides them together. This is a process that can change one element into another. Typically bombardment of an atom with a high energy particle such as alpha or beta. For example, Rutherford used alpha particles given off from a natural decay process to bombard nitrogen-14 and create oxygen-17. This is a pretty famous process. Showed that you could change one element into another. You take nitrogen-14, bombard it with alpha particles, and you get oxygen-17. All oxygen atoms have 8 protons. There must be something else up there, I think, because the mass numbers, let's see. No, neither of them balance. I get 1 and 1. P, proton. Whenever I think 1 and 1, I think basketball, shooting free throws, but in this case, it's here's another example. If we bombarded uranium-238 with alpha particles, a neutron plus another nucleus are formed. Write the reaction. Could be straight off your next exam. This type of question. And I guess the only thing that you have to know besides how to do nuclear reactions for this part is you do have to know your particles. You have to know how to write an alpha, a beta, a positron, a neutron, and a proton. Unless they're on your conversion equation sheet, which I'll have to double check. What element would this be? Plutonium, Pu. courses about turning uranium into plutonium, making bombs from it, using it in nuclear reactors. That's not what we're going to talk about in the last few minutes. Let's see, we'll get as far as we can in this. Is using nuclear transmutation to make a specific isotope. And if your question is, why are we covering this? It's, we're going to talk about, well, this is in preparation for next week's lab. Next week's lab is nuclear chemistry. We are doing lab next week. But then this is going to show us how to make an isotope that could be used in radiation therapy. And so the process starts like this. So stable iron-58 is bombarded with a neutron to form what? And if this were your exam, it would have to say to form what single nucleus, because it's not clear that one thing will form or two things. Or what single type of nucleus. And you will be expected to know. Unstable iron-59 decays by beta emission to form the stable product blank. Please do remember that beta particles, they are electrons formed in the nucleus, and they do have -1 as their number of protons. We look up on the periodic table, and that is cobalt. Stable cobalt-59 is then bombarded with a neutron to form one thing. Cobalt-27. Oh yeah, cobalt-60, good. So here's our cobalt-60. Cobalt-60 decays by beta and gamma emission, but we're going to write it just balancing it for beta. Cobalt-60 decays by beta emission. To make, looks like nickel-60. And cobalt-60, that's one of the nuclear sources that we will have in the classroom, in the lab next week for our nuclear chemistry lab. The beta particles that are emitted here can be aimed at cancerous tumors. Tumors are more susceptible to radiation because they are quickly dividing cells. This is how they've been doing it for 50 years. It is only slightly more improved since then. How many people know somebody in their life who have undergone radiation therapy? I do. And anytime you take radiation, let me say one more thing. Anytime you take radiation, whether it's at an airport scanner, yes, that's radiation from an X-ray source, or to fight tumors, you're always thinking risk versus benefits. Anyway, we'll pick up there next time. As we are out of time. In fact, I'm a little over.